Hey there everyone, welcome back to the Water Quantum Computer Series. In the previous video we went over Deutsch's algorithm part 1 where we were analyzing the problem. And now in this video we're going to be going over Deutsch's algorithm part 2, the solution. Alright, so before we do go in, and before we do go in our video review, I just wanted to say that this is going to be the last video of this series. So I really do hope you guys have had a fun ride so far. I have too. And this video, it is a little complicated, and really if you don't understand it, it's fine. You don't need to understand it. Even I had some difficulty understanding it too. So seriously, it does not matter if you don't understand anything. I mean, the very fact that we have been through all the videos is a good thing, right? So other than that, let's cover what we're going to see in this. So we're going to have a recap on our problem that we had faced in our previous video. And then we're going to do a simple review on what is Deutsch's algorithm, the Hadamard gate, the pre-outline of our algorithm, construction of our algorithm, of our quantum algorithm. That will be in two parts, and our case 1 where f of x is constant, and our case 2 where f of x is balanced. And then we're also going to be seeing what the resultant is and the algorithms in Python. All right, so why don't we do a recap of the problem that we had faced? Right? So we had a function f of x, right, that took two inputs of 0, 1, and having two conditions of being balanced or constant. But the problem or task was that how we determine if f of x was to be constant or balanced, right? And of course, there's a way to use a quantum computer to go faster to solve this problem, but how, right? Well, the solution is Deutsch's algorithm. So what is Deutsch's algorithm, right? So the Deutsch's Joza, I'm not sure if I pronounced his name correctly, but that algorithm was made by David Deutsch and Richard Joza in 1992, and it was the first ever example of a quantum algorithm that is significantly faster than any classical computer run. And essentially, we have a black box of a quantum computer, which is called the oracle, which implements a simple function of f of 0, comma 1 to n, which is just 0, comma 1. And what it is, it takes the n-bit binary values in input and returns either a 0 or 1 of each value. Now, this is an indication that the function is either constant or balanced, right? So really, we would determine if f is constant or balanced by using the oracle, all right? So first, we need to understand the Hadamard debate, right? The Hadamard gate. So we will need to use the single qubit Hadamard gate, which takes either qubit of 0 to 0 plus 1, square root of 2, over divide by square root of 2, and 1 to the state of 0 minus 1, divided by the square root of 2. And that would result in a matrix looking like this, just like that, right? Now, in our pre-outline of our algorithm, we would need to also implement the function f of x to be either balanced or constant. For each of these cases, we would need to make sure that the specifics of the output are hidden from us. For example, if the function is a constant, right? We do not want to we don't want to be sure if it is a constant at 0 or at 1, right? And if it's balanced, we don't want to be sure if it is the identity or the flip operator, right? We will use like random numbers to help with this, right? So what we're going to do now is we're going to construct our quantum algorithm as it follows, right? So what we're going to have is we're going to place our two qubits in as states 0 and 1, and we're going to apply the Hadamard operator to each qubit, right? So then automatically, again, it is just another one of your operators, but it's kind of more complicated, right? So again, we would have 1/2 of 0 plus 1 times 0 minus 1, and then this would just equal, if we expand it, 1/2 of 0, 0 minus 0, 1 plus 1, 0 minus 1, 1. All right. That's the state that gets achieved. All right. Now, the construction of our quantum algorithm for part 2 is that the operator that reads the first qubit of x gets mapped by the second qubit of y to get y plus f of x modulus of 2. Now, for this, though, we'd have to achieve the state of 1/2 0, 0 plus f of 0 minus 0, 1 plus f of 0 plus 1, 0 plus f of 1 minus 1, 1 plus f of 1. And all the additions would just be modulus of 2, right? And then when we apply the Hadamard operator in the first bit, we would get a resultant of this state right here that I don't really want to read out because it is pretty long. But yeah, and then the final step is really just to read out the result that is obtained from each qubit in each case. So case number one would be that f of x is a constant, right? So f of 0 would be equal to f of 1. So it's either 0 or 1. And then it applies that f of 0 plus f of 0 is equal to 0 plus f of 1. And 1 plus f of 0 is equal to 1 equal to f of 1. The above output state then separates into, um, again, it is a pretty long state, right? But yeah, it's essentially the state right here. And then the reading of our first qubit just gives hat of 0 plus hat of 1, which is just equal to 0. Right, so that was a lot. Okay, again, it's fine, but this is just what shows uh, kind of the step-by-step of our f of x when it's constant. Really does it resultant is what matters. Now, case two, when f of x is balanced, right? Remember, we had two conditions that we'd introduced at the start. So then what happens here is that f of 0 is 0, and what it implies is that f of 1 can also be 1. Or if f of 0 is equal to 1, it would imply that f of 1 is equal to 0. Now, the above state then also, using this state over here, separates into this whole humongous state over here, right? But it's just the reading that is different. So the reading of the first qubit would just be equal to 1, whereas here the reading of this first qubit was equal to 0 when f of x was constant. All right, now the resultant, right? Now this shows that f of x is constant. Then the algorithm makes the first bit become 0. And if f of x is balanced, then the algorithm makes the first bit become 1. So we would have shown that this algorithm tells you whether the function is constant or balanced with just one iteration through these operations, which is what we'll be showing in our Python activity. Now, this is really what Deutsch's algorithm is, right? And when we do the scaling up to n amount of inputs, we would only need to apply the Hadamard operator in n amount of times, and then the function f of x once, right? And then obviously the Hadamard operator more, right? And then therefore our own quantum algorithm will get scaled, right? And then our classical algorithm would also have to be scaled the same amount of times, right? So we would have taken an exponentially difficult problem to solve classically, and we would have solved it in kind of a polynomial time with the quantum computer, right? So now let's go to collab and let's go ahead and frame some our algorithms, right? I mean, what we're really going to be doing is we're going to be defining a few useful matrices, right? And then we're going to demonstrate how to use them in Deutsch's algorithm, all right? So let's just go here to our fancy quantum algorithms Python notebook. Then let's create a. So what we're going to be doing is we're going to be creating a Hadamard matrix for the Hadamard operator, right? Just like how we created for the flip operator, anything, right? So so it's just going to be 1 divided by, actually, before I do that, let me just import numpy as np. So we're going to have Hadamard is equal to 1 divided by np dot square root of 2 times np dot array. And then what we're going to have, our own two-dimensional array here. So we're going to have 1 divided 1 comma 1, and then we're going to have 1 comma negative 1, and that is really just the matrix that we had seen right here. All right, that's our Hadamard gate matrix. So all right, so let's go here, and all right, so that's our Hadamard matrix, right? And then if we just print Hadamard, we would just give this a few seconds. Yeah, this is our matrix that we get now. So this code block, right? It defines again, this new code block that we're going to create, right? It's going to define our two classes of functions randomly, right? We're going to have a balanced operator of f underscore balance that is either the identity or the flip operator, and then we're going to have a constant operator of f of constant, right? That matches both of the states to 0, 1. So and again, both of these cases are chosen with the help of a random number, as we had said, so that they are given at any point. So one thing that is that we are not sure of the two output maps that we are working with in each case, but it's only that they're either balanced or constant. All right. So for this, though, we are going to need our identity and flip matrix. So just in case, I'm just going to of our just gonna import this quick, but I'm just gonna paste in our identity and flip matrix here. All right, so that's our identity and flip matrix that we had made like a while ago, somewhere over here. Now, simply what we're gonna do is we're gonna be generating a random number. Uh, so here's a new Python function that we can use. It's called random integer. Simply, we have random number that is equal to number pi of random dot random integer, and then simply you have two parameters. You have I can either choose 0, 10. Now this np.random.random function, what it does is it takes a random number between these two integers. So what we're going to be doing is if we just print random, which stands for a random number, we would get something like 5, right? Or if we run this again, we'd get something like 3. We'd get something between 0 and 10, right? So in this case, since we do have our 2 qubits, we're just gonna have 2, right? And simply we're gonna now again we're gonna have our balance operator, right, which is f underscore balance. That is either the identity or the flip operator, right? So simply this will just be random number times the identity plus the 1 minus the random number, and then we're gonna just gonna be multiplying this by the flip matrix. All right, and then we can just do, or we can just print. We can just say, okay, our f underscore balanced. We're just gonna mark what our f underscore balance is, right? You know what? We can also just have a new line too, just to make it a little more organized. And then we're gonna have that. All right, so when we do print this, all right, as you can see, we have our f balanced. This is our balance that is either the identity or the operator, the identity operator or the flip operator, right? And that's the matrix that it produces. And then just add another line here. And then for our f constant, right? This maps both states to either 0 or 1. So f underscore constant is equal to the random number times number pi dot array. And then again, simply this is just going to be another two-dimensional array. So again, this two-dimensional array, like as we had said, the mapping of both states would go either to 0 or 1, but these cases are again chosen with the help of the random number. So which is what we will be explaining in a few seconds. So, and then our two-dimensional array would just be here. So we would just be creating our separate matrix here now. And 0, 0. All right. Now we do need to apply our a second state, right? Because again, it does have either states of 0 or 1, right? So then we are going to have plus 1 minus the random number multiplied by the array. Oops. Number pi dot array. And then we're gonna have our first row and our second row. Oopsies. Right? -1, comma, -1. And then, you know what? All right, since I am too lazy to like type out, I'm just gonna like this constant. So we're just gonna print out our constant, right? There. All right. Boom, and that's our f constant. All right. So again, both of these cases, using the help of the random number at any given point, we don't know the two output maps that we're working with in case, but it's only that they're either balanced or constant. All right. So now what we're going to be doing is we're going to be finding the Kronecker product of the identity and the balance matrix, right? To get the balanced function result, right? We're going to be testing it. So we're going to have our f total is equal to mpi mp.cron. If you don't understand what Kronecker is, go back to the Kronecker product video, and it's a more detailed, there's a more detailed explanation in there. F underscore balanced, right? And then simply if we print this. Yeah. So again, we just use this to test the balance function result, right? And then now we can do the constant one, right? So we can have, let's say, f total was, let's say, equal to np dot cron identity, again, of course, the identity operator, right? And constant. And then if we were to print Mr. Total, here's what we would get for our constant, right? So it's kind of the same thing as the chronicle product. You could see it aligning here, right? 0 in this first matrix right here. Yeah. Okay, so now what we're going to be doing is we're going to be defining our Hadamard operator again. And then we're going to be using our creating an algorithm, just using our chronicle product by applying the Hadamard operator to 2 qubits. And then we're going to be map muling our total by our algorithm, right? But so far, we're just doing it for the balanced one. So for now, we could just, is that word? Yeah, there. We can just comment that out. So that f of total is the chronicle product of identity and the balanced. Then now what we're going to do is we're just going to go back, get our Hadamard operator from here, put it right there, and then we're going to be defining our algorithm. So we're going to have algorithm is equal to np.cron Hadamard. So simply what this does is that it just applies the Hadamard operator to both qubits, right? And then we're going to apply this to f of x next, and then we're going to do that by doing np.matmule, just matrix multiplication of f of total and the algorithm, right? And then once we have that done, we're going to define algorithm again. Define it again. And again, and we could do np.matmule and get the chronicle product of the we'd use our Hadamard the algorithm. So simply finally we would just apply the Hadamard operator to the first qubit only, right? Apply Hadamard to first qubit only, and then we print algorithm. Yeah, so that's what we get. All right, now we're just gonna, the final step is just to process our input state and our output state, all right? And we're gonna see the correlation to our algorithm matrix right here, right? So our input state for the function of f of x, right, would just be the chronicle product of I would simply insert 2 qubits, right? So here we would have mp.array. We would be creating our matrix, right, of this 1, 0. Then, and then we'd be doing it of, let's see here. That, yeah, and then comma. Array. And then this would just be 0.1. And then our output state, quite the lengthy process here, would just be np dot matmule algorithm and input underscore state, right? So we're just applying the algorithm that we have constructed here and matmuling it, or matrix multiplying it by our input state, as that's the result we would get. So all right, so once you print this out, yeah, so oopsies, wait. Uh, uh, huh. Seems like do have um, ah seems like I know why. So we map muled total and algorithm, but I think we took the Chronicle product. Da-da-da. Okay. Actually, okay, maybe just all right. Yeah. So here's what we have to do back here. Right? We had to apply our Hadamard operator to both qubits, right? And then we had to apply our f of x next, right? Our total function, and then finally we would apply the Hadamard operator to our first qubit. So when we do get this, okay, yeah, I think it just might be something with that Python port right there. Yeah, all right, it's fine. But simply that's what we would get, right? We would have our own input state of our qubit system, and then we would get our output state, right? So that is really Deutsch's algorithm in its entirety. I really do appreciate you guys staying with us for this time, and it really has been a ride. So yeah, if you really, this was a pretty complicated video, especially for me. But yeah, let's just be glad that we were able to at least understand some basic components of this vast subject of quantum computing, right? So yeah, other than that, everyone, please have a great day.